Okay, now we begin with the goal of getting all our parts together so we can solve a type of problem that's shown here. So this typical configuration has a number of things. It has a single inlet, a single outlet. The fluid moves through a constant diameter pipe, and there's a pump within this control volume that we've defined that contains the entire pipe, the inlet, the outlet, and whatever pumps or turbines that are within it. Now, this is the energy equation that we've just developed. And if we look back on what we have here, we know everything except for how to deal with this loss term. So we need to determine a method to evaluate how this loss term shows up. So that's what we're going to do in the next couple slides. All right, so what we're going to do here is first consider a simple example. Right, so this would be something that you could technically run in a lab, and these are the type of experiments that were run. So we have a pipe, it has a constant diameter, and we have pressure taps at P1 and P2. So the pressure taps are a distance of length L apart, and we can vary these types of parameters. So the fluid that's running through the pipe, we assume that we have pipes of a bunch of different diameters, and we can vary the flow rate, which of course then is the flow velocity as well. If I divide the volumetric flow rate by the diameter of the pipe, I'll get the average velocity. And we also assume that we can vary the distance between the pressure taps. So if we do this and vary all of these parameters, what we find out is that for the flow moving in the direction shown, so we're moving from left to right, we would get a situation where there's always a change in pressure, always. And we find that P2, the downstream pressure, is always less than P1. And the other important result is it's not an arbitrary change. The change in pressure is a linear function of the separation distance between the pressure taps. So we find out that P2 minus P1 divided by L is a constant. And of course, we could plot that. If we knew our location, we knew our pressure, and we find our other pressure, and we could draw a straight line between them, getting this slope of delta P over delta L. And of course, what we've done is we've changed the distance of L, so we have multiple points in here to verify that this is indeed a linear line. And of course, what we've done it for different diameters and different fluids, and we keep getting the same result. So if we go ahead and then look at this configuration, what we have is it's horizontal, so Z1 equals Z2. Since the diameter doesn't change, we're going to get that V1 equals V2 because the flow rate's constant. If the diameters are the same, flow rate is V times area, so we get that V1 equals V2. There's no pumps or turbines. So if we go ahead and apply the energy equation, we find out that now these terms are not zero, but this term cancels with that one because the velocities are equal to each other. This term cancels with that term because there's no elevation change. And now H pump and H turbine are zero because they're not there. And what we're left with is an expression that the loss term is the pressure loss divided by gamma. That gives me the units of length. So from this experiment, we conclude two things. One, that there is a pressure drop, and the pressure drop is proportional to the length of the pipe or the distance between the pressure taps. And from the energy equation, we can now write that the loss term is equal to delta P over gamma, where of course gamma is equal to rho times G, just to remember that. It's the specific weight of my fluid. So we now know that the So we now know that the viscous effects cause a pressure drop, and we have some way of relating it. So loss will result in a pressure drop. So now our goal is to obtain an expression for this loss term that can be used to determine the pressure loss in terms of known fluid quantities. So if we know the fluid and we know the flow rates, we should be able to. So our goal now is to obtain an expression for HL that can be used to determine the pressure loss in terms of the known fluid, so density times density and viscosity, the flow rate, and the pipe dimensions. So for laminar pipe flow, we are going to be able to get an analytical expression. So we're going to start with F equals ma, so a kinematic analysis of a cylindrical fluid element, and we're going to be able to end up with an analytical expression for HL. However, for the turbulent flow, we're going to have to use a dimensional analysis because of the complex nature of the turbulent shear stress. Okay, we've gone over this in class, but I just want to make a summary of how we obtained this viscous loss term for laminar pipe flow. So again, we started with a free body diagram of a cylindrical fluid element, and we note that there's a pressure difference on either side of this element, and that's what's driving the flow forward. And that driving force is going to be exactly balanced by the shear stress terms. And in this case, in the analysis, we restricted our analysis to Q equaling a constant. So if Q equals a constant, that gives me the average velocity as a constant. And then for fully developed flow, we also find that at any radial location, the velocity is also going to be a constant. So that means that the acceleration of the fluid is zero. So we were able to do essentially a static force balance on the element because the sum of the forces have to equal zero since there's no acceleration. And we got two major results. We found out that the shear stress within the fluid is a linear function of R, and that the shear stress is zero at the center of the pipe and it achieves a maximum value at the wall. And then we find that the delta P over L, this constant value that we just showed, is going to be equal to 4 times the shear stress at the wall divided by D. And we didn't do anything in this analysis that restricted the result to laminar. So this is applicable to laminar and turbulent flows. But then how do we get to the laminar case? Well, the laminar case allowed us, or when we consider laminar flow, we have this expression where the shear stress has an analytical relationship to the velocity. In this case, the shear stress as a function of R is equal to mu, the viscosity, times the radial change of the velocity, so du dr. And now we were able to use this expression. I don't need to go back over it again. And we were able to get the following results. So we got the velocity, we got an expression for the fully developed profile. The velocity is a function of R. And we note that when R equals 0, this whole term goes to 0. So this term is the maximum velocity. From that, we were able to get the volumetric flow rate. So we have from the maximum velocity, I don't write it out here, we were able to get the average velocity, which is 1/2 the maximum velocity. And we're able to utilize that in obtaining an expression for the volumetric flow rate. And then finally, the average velocity. So the average velocity is half of the maximum velocity. You can see that here. One is 16 and one is 32. And then if we, for the rest of the discussion, whenever we write V, we'll just assume that it is the average velocity. And then we have an expression for the change in pressure. So within a circular pipe with laminar flow, constant flow rate, we're now going to have an expression for the pressure drop. And I could divide these both through by L, and that would give me the pressure drop as delta P over L, but we know that this is a linear pressure drop. All right, so now we can take these results, and now we're essentially manipulating them to obtain this required expression for HL, and we'll find out that the required expression is sort of being driven by the analysis for the turbulent form that comes from dimensional analysis. But essentially what we're doing is we're doing some machinations here. So if we multiply both sides by or we divide both sides by the specific weight, 1 over rho g, and then I multiply the right-hand side by 2v over 2v, multiplying it by 1, I get this expression. So the 2 over here multiplies by the 32, then we get mu divided by rho v, one of the d's, and that's going to give me the Reynolds number. Then we have L over the remaining d, and then we're left with v squared over 2g. So what we end up with is this expression, right? It's delta p over gamma, which we've shown as being equivalent to the head loss, or the loss term, is going to be equal to 64 over the Reynolds number, L over d, times v squared over 2g. And then we are going to take this constant term, right? It's a constant term for any given flow rate, right? As I change the flow rate, I will change the Reynolds number due to the velocity, and we're going to term that as being the friction factor. So this gives me this form of HL, my frictional loss, or due to viscous forces, is equal to some friction factor times L over D times V squared over 2G. And in this case, for laminar flow, that friction factor is equal to 64 over the Reynolds number. All right, so now we can go ahead and summarize how we get the expression for the viscous loss term HL for turbulent pipe flow. So we've already shown that from the previous that we can utilize these two expressions, or that these two expressions are true, that there is a linear change in the shear stress as we move out from the center to the wall, and that delta P over L is still going to be a constant. But here's the issue. There's not a simple expression that relates the shear stress at any given radial position to the velocity at any given radial position, which we have for laminar flow. So since we don't have that, it's just not possible to obtain the analytical expression for HL. So what we do is we employ dimensional analysis. Okay, so now before we do that, I just want to note that, in the following discussion, we're going to have these functions, f1, f2, f3, and these are arbitrary unknown functions. So even though we don't know the form of the functions, what they are used for is that they signify that there is some type of functional relationship between the terms of the function, so the arguments of the function. So in example 8.4 of the text, they give the full analysis of applying the Buckingham pi theorem to a situation where we're looking for the effect of what's causing the pressure drop. So if we summarize here, the analysis, right, someone who actually has studied this would say that the change in pressure as fluid flows through the pipe has some relationship to the diameter, the length of the pipe, the type of fluid, the viscosity, and the one term that we didn't add in terms of laminar flow, because as it turns out it's not important when we're dealing with laminar flow, is this term that is for the roughness, that describes the roughness of the pipe. So it's E over D. The epsilon value is literally the height, or the measurement of the average surface roughness. So you can take a look in the book, but that E has a value of length divided by the diameter is the length. So now that's the functional form, and then that gets the value of f1. Now if I rearrange it so that everything equals 0, I'm essentially taking, instead of having a function that's going to end up equaling delta p, I now create a new function where delta p becomes one of the variables, and the whole function now has to equal 0. So while the function 1 of those variables was going to equal delta p, I now create a new function that includes delta p, and that function has to equal 0. So that gives me 7 variables. There's only 3 units, mass, length, and time, and that's going to give me my 4 pi groups. So we go through the set of dealing with the repeating variables and going through the math, or the steps rather, and we end up with a pi group 1, a pi group 2, pi group 3, and pi group 4. So the first one is delta p over rho v squared. The second pi group is the Reynolds number. We would kind of expect that. And then the third is L over D, and the fourth was actually a dimensionless parameter when we put it into the function. So it's epsilon over D. So we find out that this function f2 is a function of these pi groups. So here's this arbitrary function f2, and all that equals 0. So now what we can do is I can pull out this term, and it's going to create a new function, but now we could say that delta p is equal to rho v squared times a function that now depends on the Reynolds number, L over D, and epsilon over D. So now the next step is we say, and again, this is by doing a dimensional analysis. Well, we've already done one that we've shown by experiment that delta p is a linear function of L. So we see that that's one of the parameters in this function f3. So we say that we can pull that out. In other words, we already know the functional dependency on the length. So we pull that out, and we end up with delta p is equal to rho v squared times L over D times a new function that just has the Reynolds number and epsilon over D of it. We have this expression for the laminar analysis, so we want the turbulent form to look like that. So we know that the head loss is going to be delta P over gamma. So we're going to multiply this expression now by 1 over rho G. And when we do that, we end up with this expression. So once we've multiplied everything through by rho G, we now get that the head loss is V squared over G, L over D, times this unknown or as yet arbitrary function. So now we want to match the laminar form, so we need V squared over 2G. So we multiply through by 2 over 2, right? That's multiplying by 1, but what we end up with, so that gives me my V squared over 2G, but now we're ending up multiplying this arbitrary function f4 by 2, and that creates a new arbitrary function. It doesn't really matter, and that gives me my final, well, my almost final form of the head loss. Okay, so the terms in front, my V squared over 2G times L over D, matches that of the laminar form, but now we would like to get ourselves to what the friction factor is. Okay, so our final step is to recognize that the functional relationship between the Reynolds number and E over D is the friction factor for the turbulent pipe flow. So we can now take this whole term and call it F. So the form of the viscous loss term is the same for both laminar and turbulent flow. So the loss term is F L over D V squared over 2G, except for how the frictional term is defined. So for laminar flow, it's 64 over the Reynolds number. For turbulent flow, it's this function. And that function comes from experiments, and we can evaluate it knowing if we know the Reynolds number for the flow and the value of epsilon or epsilon over d, the roughness, we can go to this Moody diagram, which again is completely created via experiments, and or we can utilize this equation developed by Halen that gives us a pretty good approximation of the values on the Moody diagram. So I have a quick example here. So for given pipe flow conditions, say we have the Reynolds number ends up being 10 to the 5, and we have epsilon over d equals 0.001. All right, so we go there, and in the diagram, we find out that we start here at Reynolds number being 10 to the 5th. We go up until we cross the line where the friction factor is 0.001, and the crossing is here. We come across to where the friction factors are defined, and we end up with a value that looks like being approximately 0.0223. All right, if you want to program it into your calculator, you can also utilize the Halen equation. Again, for the life of me, I never understand why they write the Halen equation in this form, because it's harder to use. This is the form that you'd want to utilize because you just put your numbers into it. Only thing I'll point out is that you have to use the log of base 10. So here is my value for the E over D. There's my value for the Reynolds number. You take the whole argument and you raise it to the -2. So we end up finding that we get a value of 0.0219662, which rounds to 0.022. So either of these will give you a value. All right, so I'm going to stop here, and then the next thing to do is now to run some example problems of how to evaluate a system now that we can explain what's going on with frictional losses. The one thing that I haven't covered here are the minor losses, and I'll add that in when we do the example problems. But again, we've looked at it in class that we make the minor losses look like the major losses, which is F L over D V squared over 2G, by simply writing, and let me write it down here on the bottom, that the minor losses will have a form of H minor will equal the sum of these K values times V squared over 2G. And these are values that we need to look up in tables. And there'll be one of these values for every elbow, expansion, contraction valve in the system. And these all just get summed together, these coefficients, and they end up multiplying V squared over 2G, and that gets added into our loss term in the energy equation. All right, so we'll look at a couple of examples, but for right now, we've done the major bit of the analysis.